everyone. My name is Rebecca Bickham, editor of NACE International's Materials Performance magazine. And joining me today on the podcast is NACE member Darby Howard, who is principal engineer and president at JDH Corrosion Consultants Incorporated. And today, Darby and I will be discussing a project of his, which involved testing, inspecting, and rehabilitating offshore cast iron pipes in San Francisco. Hi, Darby. How are you?
Hi, Rebecca. Yeah, I'm good. How are you?
I'm doing great. Thanks for being here today. So
You're welcome.
this project is one that we featured a year ago in the August 2019 issue of Materials Performance, and I wanted to have you on the podcast to talk about it because it's such an interesting project. So let's start off with you giving our listeners a brief overview of the project.
Basically, we learned about this project from one of our clients, City and County of San Francisco. They happened to mention to us that there were some outfall pipelines in San Francisco that were going to be replaced to the tune of many millions of dollars because they could not be adequately assessed as far as corrosion damage. And when we heard that, we told our client, hey, what's the situation? Let's take a look at this, because maybe we can do a proper assessment so you don't have to end up replacing these things. And so he gave us the information on it. We did a little digging and told him that, we have some techniques that we can use, and we've looked at projects like this in the past, and we've done a few innovative things that we feel like we can do a proper assessment, sufficient enough that if the results come out like we think they're going to, it will save you millions of dollars because you will not have to replace these outfall pipelines, but you can save them instead and perhaps do a little bit of remedial work instead of replacement. So the real goal was the fact that their justification to replace the pipelines was strictly based on the fact that they could not be adequately assessed. And so that's what kind of got our attention, and we said, wow, that's not a great reason to be spending millions of dollars, is because you say you can't adequately assess them. So that's really what got our curiosity up, and we looked at this and said, yes, we can do this. And so we embarked on a scope of work to basically assess them. So that's how the whole thing got started.
Okay, great. So can you tell me a little bit about the different phases of the project and how long it took?
Yes. So there were several phases on this. Because these are outfall pipelines, they're under piers 33 and 35 in San Francisco. And to assess it, a couple things needed to be done. We needed to be able to go in on the inside of the pipeline and see how much corrosion damage has occurred there, and we needed to get to the exterior of the pipeline and see as well. And these pipelines are, there's 4 pipelines, 2 under Pier 33, 2 under Pier 35. Each are 4 feet in diameter, so 48 inches in diameter. And they go out about 800 feet and then drop down into diffusers. And the diffusers are actually made of ductile iron. But this is very old cast iron. And one of the reasons that somebody before us had said that they couldn't adequately assess these pipes is because it is hard without doing destructive testing, in other words, drilling holes in cast iron pipes sometimes to really assess how much corrosion damage has really occurred. So what we decided to do was to go down there, take a look at them, and we've had a lot of success working with cast iron. It's just been one of those things that we've been dealing with for years, so we had a high level of confidence that we could go down there and do some ultrasonic thickness testing on them and get some good results. So when we got down under the piers and started looking at them, of course, they're heavily encrusted with barnacles, so it's really hard to even see the pipe. You got to scrape the barnacles off first to even get to the pipe. And then we did see it was cast iron, and we started to do ultrasonic thickness measurements. And the issue we have is the issue everybody has with cast iron, and that is how do you know your measurements are accurate? Because there's no calibration block designed for old cast iron. Cast iron is made in such a way that really each lot of cast iron is a little bit different, especially old cast iron that's 70 years old. None of the manufacturers of ultrasonic thickness meters has calibration blocks for cast iron, And every time you ask them a question like, well, how do I calibrate the cast iron? They say basically you've got to get a piece of cast iron and calibrate to something of known thickness, but they don't know what velocities to use offhand because cast iron is so varied. So what we did is we got under the piers and actually found an abandoned piece of cast iron pipe that was installed at the same time as the rest of this pipe. And then in later years, it was abandoned because they rerouted the pipeline. So we knew it was from the same vintage, the same age, and we asked San Francisco's permission to cut out a piece of the pipe. And fortunately for us, they said yes. So we cut out a piece of the pipe, we took it to a machine shop and had a calibration block made. So now we knew that we could actually calibrate our instruments to the exact type of cast iron we were dealing with. And that way, when we got onto the exterior of the pipe and started doing UT testing, we had a high degree of confidence that our numbers were right on. Within a few thousandths of an inch, we knew we were right on. So that's what we did. We made the calibration block and then went under the pier to test the pipes. Now, another reason it was said that this was not easy to assess is because the pilings under piers 33 and 35 are very close together. In a lot of areas, there's only 6 feet of space between piles, which means you can't get a very big boat in there. And there's waves, and so if you try to get in there with an aluminum boat, it's going to bang you around, and because there's always waves, because of boats going past or because of tides coming in and out. So we purchased the Zodiac, which is an inflatable boat, and we used AstroTurf. We took AstroTurf and put it around the perimeter so that the barnacles wouldn't cut our boat and sink us, and it was narrow enough that we could squeeze between these pilings enough to be able to get us under the pier and all the way to the outfall pipelines. And then my guys could rope off onto those pipelines, scrape off barnacles. So we were able to get to the exterior of the pipeline, scrape off barnacles, and underneath the barnacles we found, surprisingly, very little graphitization, which, since this pipe is in the splash zone, the bottom of the pipe is about at mean low water level, which means it's always wet twice a day during tides. We thought that we would find a lot more graphitization than that, but we were able to determine that the barnacles and the graphitization that had developed about 1/8 of an inch actually were protecting the cast iron pipe from additional graphitization. So then we got in from the exterior and did a lot of UT work. So then we knew that we might be missing some critical areas, so we had to really get somebody inside the pipe to see if there were any areas where there was large amounts of graphitization or corrosion on the interior of the pipeline. So to do that, we hired a diving company and actually sent divers into the pipelines. So the divers entered through manholes in the piers and dropped down into the pipes, and then went along the interior, and anytime they located an area of corrosion, they would scrape it out, measure how much pitting they found, and anything that was significant, they would then communicate to us. We would have a boat on the outside while the divers were on the inside of the pipe, and they would indicate to us where they were, and then they had a device that had a transmitter, and we had a receiver on the exterior. We would line them up so we knew we were on the exact spot, and then we could do an ultrasonic thickness test at an area where it was the thinnest. So where we found maximum corrosion, we would do UT testing right there to try to get worst case scenarios. And that worked actually very well, putting the diver in there. And one of the funny things that we learned out there is that when you suit a diver up, to go into San Francisco Bay water, which is about 52 degrees Fahrenheit, he wears a wetsuit, but a very thick wetsuit, and he's got a big helmet on, and he's got audio and video equipment with him. It weighs a lot, so he's crawling through the pipe. He's sweating. It's hot work. It's hard work dragging his basically his umbilical cord, 800 feet down the pipe. But when the tides came in, and at high tide, of course, this pipe is underwater, which means the pipe fills up completely. And during the testing, the tide was coming in, and as I was talking to the diver, he said it's getting easier and easier and better for him, because he says, I'm starting to float. Once the water started coming in the pipe, for him, it was easier to maneuver in the pipe because he wasn't dragging everything and he wasn't having to pull his own weight and all, and the water was cooling him because he was sweating. So funny how when you're doing outfall pipelines like this, as far as from a diver's perspective, actually in a way it's easier for him when the pipe's full of water rather than dry like we always assumed. And these guys actually work very well in either wet or dry conditions. So anyway, just that was a little sidebar. That's something interesting we found out. But we enjoyed working with the divers. We were able to get really good data on the pipe and determine how much metal loss we had from the ID of the pipe and the OD, so the interior diameter and exterior diameter. And we found that overall, for a 70-year-old cast iron pipeline in a splash zone in under piers in San Francisco, very little corrosion loss was found. So we were able to get enough engineering data to be able to definitively tell San Francisco that the structural capacity of the pipelines were not diminished in any way significantly enough to limit their ability to be used as outfall pipelines, which was really good news. So it basically tabled the whole conversation of having to replace these pipelines. And instead, what we decided to do, along with San Francisco's assistance, was to put a new liner on the interior of the pipeline, a new epoxy liner, and you put cathodic protection on the exterior of the pipeline. And the cathodic protection system was going to consist of galvalume anodes installed on sleds on the exterior of the outfall pipeline. So that's what we did, and San Francisco was very appreciative of the fact that they did not have to replace these outfall pipelines. So
great, and saved them millions of dollars
kind of a
as well.
long answer to your question, perhaps.
No, that's great. So another unique feature about the project is the location. So not only was it in the San Francisco Bay, but it was right next to a famous tourist attraction, Pier 39. What was that like?
Yeah, that was great. You're right, because the odd numbers go north from the bridge, even numbers go south from the Bay Bridge. So you got piers 33, 35, and there isn't a 37, it just goes to 39. 39 is, of course, a world attraction. All tourists come from all over the world every year to go visit Pier 39 to see the seals. The sea lions are on docks out there, and there's a lot of famous restaurants. It's quite the area, quite the tourist area. And so working next door seemed like most of the time we were trying to shoot for low tide, so we had to have complete access to the pipeline. And the time of year we were working, most of the really good low tides were very early in the morning, say, 4 o'clock to 7 o'clock in the morning would be low tide. So we were always out there mobilizing at 3 in the morning and getting to work. So typically, by the time we got back up to a fairly good high tide would be about, let's say, 9 o'clock in the morning, maybe by 10 o'clock. We had to be out from under the piers because the tide was coming in so far, and we were starting to lose our ability to maneuver the boat in the piers at high tide. So we had to basically get out of there. So we typically, by mid-morning each day, we were done, so we could get out of the water. And we rented a boat slip over at Pier 39 to keep the boat there because this job took several months. And we would go tie the boat back up and then hike back up to the top of Pier 39 and then have a really good breakfast and kind of walk around for a while and enjoy the fact that we're down at Pier 39 in the morning before all the tourists would show up, since they didn't really show up till late morning, early afternoon. So it was a lot of fun. And one of the other things was, because Pier 39 attracts a lot of sea lions, it's the home for a pretty big sea lion population.
Mm-hmm.
They're all over the bay, and of course the sea lions are under the piers too. So one of the funny things is when you're down there floating on a Zodiac, moving along under the piers, occasionally you stumble across these sea lions who are laying down there. I don't know if they were fishing or sleeping, but they would be startled and they would roll over and look at us real quickly and then dive down. But the thing was, when you get that close to a sea lion, you realize that sea lion weighed more than, if there were, say, 3 or 4 of us in the Zodiac, he outweighed all of us combined. And we all knew
Right.
that, boy, if he decided to sink us, he would sink us. So you don't realize how big these creatures are until you're down there in the water with them, and you go, oh my gosh, these things are huge.
Yeah, that's
But
incredible.
yeah, but it was a lot of fun. Seeing a startling sea lions was pretty funny. Another problem we had was, because this is a heavily trafficked area with cargo tankers coming in and dropping off fuel to the power plants. What we found was these ferries and cargo ships would come by, and we'd have to have a lookout for them, because after they would go by, it'd be literally a couple minutes later when the waves would come under the pier. And if you're not expecting it, and a 2-foot wave hits you when you're on a raft, it's quite scary, and it's bouncing you around, and you're like a pinball bouncing off all these pilings down there. So that was kind of scary. So we always had to have a point man, someone that was a lookout, letting us know, okay, here come the waves, guys. So hang on, because we didn't want anybody getting thrown overboard. Even though we had life jackets on and everything else, we just didn't really want to end up in 52-degree water. So that made the job kind of challenging and interesting also, and kind of a lot of fun at the same time.
Okay, and my last question for you is how many more years of service do you think these pipelines have left in them, and how often are they inspected now that the rehabilitation part of the project is complete?
So we inspect the cathodic protection system annually, make sure it's doing its job, and it is. So we have to go out there at high tide to make sure the pipes are underwater when we inspect them, and make sure they're polarized adequately. And we estimate that we have at least 30 years, maybe up to 50 years of additional life for the outfall pipelines, which actually worked out really well for San Francisco, because they have in their long-term plans to rehabilitate piers 33 and 35 in the future. So they said if we could get another 30 years out of it, that would be great, because they didn't really want to have to rehabilitate until that time period. So this gave them the breathing room that they really needed to be able to concentrate on other things, and to basically push this off for another 30 years, at which time then they're going to go ahead and rehabilitate the pier, and at that time put in new outfall pipelines. So it ended up being a good project, and giving San Francisco exactly what they were looking for longevity and useful life on these outfall pipelines.
Well, thank you so much, Darby, for joining me today.
You're
Um,
welcome. This was fun. It was a great project to work on. And if I can mention one more thing that
sure.
I would say engineers choosing to listen to this podcast might find interesting, was when we were designing the sleds to float the anodes underneath the piers to protect the outfall pipeline. We had done a quick in the office back of the envelope kind of design of about how big the sleds would have to be to float these anodes, because the anodes are very heavy. They're like 300 pounds apiece, underneath the pier, and then sink them over next to the outfall pipe. But it wasn't a final design. It was just like a quick back of the envelope calculation. And what we didn't realize was that San Francisco took that and then turned it into a final design, but nobody ever actually went back and looked at the final calculations for buoyancy. So when we got out there, we found out, well, gosh, no one ever did buoyancy calcs. So the sleds, basically with the anodes on them, sank. So fortunately, the divers were pretty clever guys. They're used to floating things under piers, so they added big flotation bags to the sleds that we made, and pulled those and tugged them underneath the piers and sank those. It worked out really well. There's just a funny thing where in engineering sometimes these things sort of happen, something gets missed. In this case, it was buoyancy calculations. Who thought about doing buoyancy calculations on these things? Anyway, it was just, by the time we found out that no one ran them, it was too late, because they were already being manufactured. So it was just kind of an interesting thing where, oops, it got missed, but at the end of the day, it wasn't, ended up not being an issue at all, because the divers found a clever way to get everything under there anyway. So So just an interesting sidebar for engineers: just don't forget when you're trying to put anodes under piers and you're going to use a sled that's going to float them. Remember to run your buoyancy calculation.
All right.
So
I'm glad you
that's
added that. Thank you.
okay.
Um, so thanks again for your time, Darby, and this is where we'll end things today. Again, my name is Rebecca
Okay.
Bickham. I'm the editor of Materials Performance Magazine. Thanks for listening.